Welcome back to AI Paper Slop. We are jumping right in today with a paper called ETA, a new agentic paradigm for embodied tasks.
Yeah, no time to waste on this one.
Exactly. So for the ML engineers and researchers listening, I'm just going to give you the absolute core insight right now. We're looking at a totally new architecture called the Embodied Task Agent, or ETA.
Right, which completely ditches the whole end-to-end vision language action model approach.
Yeah, the VLAs, those models that basically try to predict, every single tiny robotic action directly from raw pixels.
Which is how almost everyone is doing it right now.
Right. But ETA acts as a high-level planner instead, and it sits inside this really strict gated runtime loop called OpenETA.
And it only uses 3 simple tools, right? Like just observe, mark point, and move veto.
Literally just those 3. And with 0 task-specific policy training, a GPT-5.6 model planner had a 90% pass at 5 success rate across 130 LIBERO manipulation tasks.
I mean, 90% on pass at 5 for LIBERO without any specific policy tuning it's huge.
It's crazy. So our mission today is to completely break down how this architecture actually works. We need to talk about why its strict runtime invariant rule is like a total game changer for AI safety.
Oh, for sure. The safety aspect is massive.
Yeah, and then we're going to look at the gritty reality of actually transferring these agents from a clean simulation over to a physical, real-world robot arm.
Which is always the hardest part, right?
Yeah.
Sim to real is brutal. But to really appreciate the scale of that 90% benchmark, we kind of have to look at the limitations of the current foundational models you're probably working with right now.
Yeah, let's set the stage, because the landscape right now is basically dominated by VLAs, right? Like RT2 or OpenVLA.
Exactly. So a VLA takes in visual observations, it takes your natural language instruction, and it just mashes it all through a giant transformer. And then it maps that directly to low-level robot actions.
Just spitting out continuous action tokens.
Yeah. Or, you have world action models or WAMs, and those try to predict the possible future states like the next video frame before they act.
But the paper really goes after these models, right? Because they have this fatal flaw.
They absolutely do. Their ability to generalize relies way, way too heavily on the coverage of their robot training data.
Right, like if the model hasn't seen a very specific textured object in a specific ambient lighting setup on that exact robot arm in the training set, it fails.
It completely collapses. And for long horizon tasks, it's just a nightmare to debug.
Because it's a black box.
Exactly. If it fails halfway through stacking 3 blocks, you can't inspect the logic. You just have a string of predicted action tokens that eventually caused a collision.
So it's basically like driving blindfolded based entirely on a memorized route you studied before you got in the car.
That is exactly what it's like.
You turn the wheel 2 degrees, hit the gas, and just pray the road hasn't changed. Whereas the ETA approach is taking one step, pausing to actually open your eyes, checking your real surroundings, and then deciding your next step.
Right, and what's fascinating here is the shift in trust. We're essentially taking absolute control away from the monolithic neural network.
Which is a big deal because we usually trust the neural net to do everything.
Exactly. But ETA hands that control over to an auditable runtime loop. It stops trusting the foundation model to just inherently learn physics by looking at scaled-up trajectory data.
Okay, let's unpack this. Because if we are taking direct control away from the neural net, how does OpenETA actually enforce that on a software level?
It uses a really strict 3-part separation of trust. So you have the agent, the interface, and the world.
Okay, so the agent is the foundation model itself.
Right. It understands the task, it manages its working memory, and it proposes a command. But it's totally quarantined. It cannot act on its own.
It has to go through the interface.
Yeah, the interface is the ultimate gatekeeper. It intercepts the proposed action, validates the structure, checks if the agent actually has authority to use that tool, and authorizes it.
And only then does it talk to the world, which the world here could just be the simulator, right?
Yeah, like using the Model Context Protocol, the MCP, to talk to the sim. Or it could be the actual physical robot.
But the crucial part is, the world doesn't just do the action and stay quiet. It returns a trusted receipt.
Oh, the trusted receipt is everything.
Yeah, because the LLM can't forge its own reward.
Yeah.
It can't just hallucinate a success log into its memory saying, oh yeah, I definitely picked up that cup.
Right. It literally has to wait for the host runtime to hand it a receipt proving the physical environment actually changed.
And that ties directly into the absolute golden rule of this whole system, which they call the runtime invariant.
Yes. The runtime invariant states that you can execute only one world-changing action at a time. And afterward, you must obtain a fresh observation before executing the next state-dependent action.
So no batching commands. The LLM can't just output a massive string like move to the cup, grab it, lift it, move to the sink, open the gripper.
Exactly. It's mathematically impossible in OpenETA. And they manage this through a system of obligations.
Okay, how do obligations work?
So imagine a pick-and-place task. The agent calls a tool to close the gripper. A normal VLA would just assume it grabbed the item and immediately swing the arm away.
Right, confident but totally blind.
But in OpenETA, the second the interface authorizes that close gripper command, it injects an obligation into the agent's working memory.
Ah, so it's literally forcing a verification step.
Exactly. The agent is now obligated to verify the attachment. It cannot hallucinate a success. It has to clear the obligation by, say, doing a tiny vertical lift and checking the force sensors.
That is so smart.
Yeah.
But if you are an ML engineer listening to this, you're probably screaming about latency right now.
Oh, 100%. The latency overhead sounds terrifying.
Right. If it has to stop, pull an image, process it, and verify after every single tiny movement, isn't this architecture just inherently too slow and compute-heavy for real-time robotics?
Well, to answer that, we have to look at the Codex mode and the LIBERO benchmark results, because theory is great, but benchmarks actually show us what's happening.
Yeah, let's talk about the OpenETA-for-Codex configuration. Because in digital coding agents, you don't give the LLM infinite tools. You give it, like, file access and shell execution.
Right, you keep it constrained. And for physical robotics, Codex uses a tiny, tiny interface, just 3 tools.
So there's Observe, which pulls a fresh visual and depth data. There's Mark Point, which I think is fascinating. It turns a 2D pixel selection into a 3D coordinate using raycasting.
Yeah, the spatial mapping there is crucial. And then finally, just move the ITO to actually move the arm.
And using just those 3 tools, they saw some crazy scaling laws across the 130 LIBERO tasks.
They really did. So using medium reasoning effort, GPT-5.6 Luna solved 47.7% at pass at 5.
Okay, decent.
Then Terra jumped up to 63.8%, but Sol just dominated. It hit 90.0%.
90%. That is a massive leap for a generalized model with no fine-tuning for the task.
And what's really interesting is why Sol did so much better. It wasn't just raw smarts. It requested the MoveVito preview way more often.
Wait, what is the preview?
So before executing a MoveVito command, the agent can actually ask the interface for a visual preview of what its gripper pose will look like at that coordinate.
Oh, wow. So it's like a ghost image of the future state.
Exactly. And Sol would actively check its gripper pose before executing. It verified its own plan visually.
Okay, that's incredibly cool. But I'm going to push back here on the viability of this whole system.
Okay, let's hear it.
Because they also ran a standard 40-task matrix baseline, right?
Yep.
And the overall pass rate there was only 14%.
Yeah, the strict protocol baseline was brutal.
And when you break down the failure taxonomy, 62.5% of those failures were just episode timeouts.
Right, it just sat there and timed out.
So if the system is timing out on over 60% of its failures, just because it's meticulously checking every single step, generating previews, waiting for fresh images, I mean, isn't it just too slow? A robot can't just freeze for 30 seconds in a factory.
If we connect this to the bigger picture, you have to realize that a timeout is a highly desirable, safe, traceable failure.
Better timeout than a broken robot, I guess.
Exactly. It's vastly preferable for an agent to pause, realize it can't safely proceed, and ask for human help, which it actually did in 19.2% of the failures, rather than confidently smashing a robot arm into a glass table because of some unverified hallucination.
Okay, that's a fair point. A frozen robot is better than a dangerous robot.
And because it's leaving this meticulous trail of logs, it opens up a huge opportunity for learning.
Oh, right. Because we have a perfect paper trail of every observation, tool call, and preview.
Exactly. So the researchers asked, if the agent is struggling with timeouts and multi-step logic, can it review its own trajectory logs to rewrite its skills and improve?
Agent self-evolution. This is like the holy grail right now.
Yeah, letting the model propose updates to its own workflow. But because it's dealing with physical hardware, you can't just let it push whatever code it wants.
Right, you need safeguards. So they set up this ruthless 4-gate promotion rule.
Right. 4 gates, an update has to pass before it's accepted. Gate 1 is the contract check. Does the code violate any hard-coded safety schemas? Gate 2 is an isolated review. It spawns a totally sterile LLM instance that has to mathematically parse the logic of the new skill.
Basically making sure the primary LLM didn't just write total spaghetti code.
Exactly. Then Gate 3 is same task replay. It has to perfectly reproduce the exact source success it learned from.
So it can't regress on the thing it's trying to improve.
Right. And finally, gate 4 is held at evaluation. It has to show objective gain on unseen tasks without causing any regressions.
Okay, here's where it gets really interesting. Do you know how many candidate updates passed all 4 promotion gates?
I do, and it's my favorite part of the paper.
0. 0 candidates passed. Broad skill edits failed to stabilize, and staged local deltas couldn't reproduce source successes.
Literally a 0% promotion rate.
Which is so counterintuitive. Most papers boast about, like, self-improving agents with charts going up and to the right. But this paper wears its 0 promotion rate as a badge of honor.
Because it is a triumph of system design, it proves the OpenETA interface actually works as a firewall.
So it was actively keeping bad code out.
Exactly. It keeps unsupported, ineffective, or straight-up dangerous improvements that the LLM hallucinated out of the shared capability library.
Because if it let those through, the robot would just start behaving erratically.
Right. The agent was hallucinating extra redundant loops or recovery rules that totally ignored the physical root cause of the failure. The firewall blocked all that junk.
Okay, speaking of physical root causes, we really need to talk about hardware. Sim2 Real. Because simulation results and strict software gates mean absolutely nothing if the robot can't operate in physical reality.
Absolutely. You have to escape the simulator eventually.
So they deployed this on a physical UR5E arm equipped with a robotic gripper.
And qualitatively, it actually worked. They successfully executed a multi-step sponge-to-tray task.
Which is pretty complex. It has to manage the contact approach, do a lift probe to verify attachment.
Right, it clears that obligation. Then it handles multi-waypoint transport and final placement, all using the OpenETA loop.
But the gritty hardware bottlenecks really showed up here, right? The Sim2 Real transfer was not perfectly smooth.
No, it exposed some major physical realities. In the simulator, your depth data is perfect. But on the real arm, they used a RealSense camera.
And real cameras have noise.
A lot of noise. The depth estimation was vastly inferior. You get infrared scattering, metallic reflections. It's messy.
And that messes up the MarkPoint tool, right?
Yeah.
Because it relies on raycasting to get 3D coordinates.
Exactly. Bad depth data means skewed pose estimates. The robot tries to grab something that isn't quite where it thinks it is.
And then there's the physics of the arm itself. The robot's strict acceleration limits are getting triggered, right?
Yeah. The real UR5E relies on internal PD controllers to manage the motors. The agent was commanding joint velocities that were just too fast for lateral grasp.
So the hardware was throwing protective emergency stocks because it didn't want to break itself.
This raises an important question, right? About what Sim2 Real actually means.
Because transferring a foundation model clearly doesn't mean you get to just skip the robotics engineering.
Right. What transfers perfectly is the task-level reasoning loop. The logic, the tool contracts, the verification.
But you still have to painstakingly calibrate the hardware limits.
Exactly. You still have to tune the PD controllers, manage the real-world payload physics, and filter out terrible depth sensor noise on the actual device.
So the AI is smart, but the body is still clunky. Which actually leads me to a final provocative thought I want to leave you with.
Oh, let's hear it.
We now have OpenETA proving that generalized LLMs can handle high-level task planning with like a 90% success rate as long as they are constrained by a strict interface.
Right. The reasoning part is basically solved.
Exactly. So does the ultimate bottleneck in achieving AGI robotics shift completely away from the intelligence of the model and land squarely on the latency, bandwidth, and fidelity of our hardware sensors and APIs?
It's a great question. Like, if the brain is finally ready, is the physical body just holding us back?
It really feels like it. We need better depth cameras and faster motor controllers, more than we need a smarter LLM right now.
Hardware is the new frontier.
Completely agree. Thank you so much for tuning in to this deep dive on AI paper slop. We highly encourage you to go read the full OpenETA paper because the failure taxonomy charts are just fascinating. See you next time.